Hello and welcome. This is our lecture video for September 16th through the 17th. We're going to be talking about how to graph linear inequalities as well as piecewise functions today. So I wanted to do just a quick absolute value graph to get started. You don't have to do this one in your notes. I'm just going to go quickly just to make sure we know how to graph these types of graphs. So what we're going to do is we're going to transform our parent function of y equals the absolute value of x using the values in the equation. So I'm just going to dot in y equals the absolute value of x, and now this shape here is going to be moved in the following ways. This 1/2 in front is going to cause a vertical compression. This +1, it always works kind of opposite of how you think, or you could think that the h value is equal to -1 here because of the minus that's built into the form. That's going to move us left 1. And then this -3 is going to move us down 3. Alright, so let's just imagine taking these points here, compressing them by 1/2. That means that their y value gets multiplied by 1/2. So like if you were a point right here at 1, now you're at 1/2. If you were up at 2, you're now down at 1. Shifting all of them left 1 and then down 3. Or you can use my trick of just moving the vertex left 1, down 3, and then using this as your slope going to the right. So slope of 1/2 would mean up 1 over 2. Imagining that axis of symmetry, making it symmetrical over that axis of symmetry. And we get a graph that looks like this. Alright, and that's what these blue dots would look like if we compressed them by 1/2, shifted them all down 3 units, and all right, or all left 1 unit. Okay, now we gotta start taking notes. Goal today is to be able to graph linear inequalities and piecewise functions. Why are we doing this? So graphing is a way to represent our answers, and sometimes your answers are in a whole region of the graph, and sometimes you need your function to change based on the x values. So we'll see what that means here. With this graph, I'm going to graph y is less than 1/5 x minus 4. Alright, so this really looks like a linear equation, but we've swapped out the equal sign for this inequality. So how is that going to affect our graph? So I'm going to do this in 3 steps. 1, we want to plot the points like a normal, in quotes, mx plus b equation. And that's it. Plot the points like a normal mx plus b equation. So I'm looking right here. I've got a y-intercept of -4. I'll put a point at -4. I've got a slope of 1/5. That means go up 1, right 5, or down 1, left 5. So I've plotted the points, but I'm not going to connect them yet. Step 2, if the inequality is a less than or a greater than, connect with a dotted line. If it is greater than or less than or equal to, or greater than or equal to, use a solid line. So we have just a less than, so we are going to connect up these dots with a dotted line. Let me make that a little more bold. We'll go with red. All right, so as we're trying to represent our solutions, points exactly on this line are going to balance this, but we don't want it to balance because the left-hand side is supposed to be less than the right-hand side. So we use a dotted line to show that we're not going to include the line itself as part of our solutions. All right, step 3. All right. If the symbol is a less than or equal to, shade below. Greater than or equal to, shade above. So now we're going to actually shade where all of the ordered pairs are that would make this inequality true. So this is a less than, so I'm going to shade below. So you can just do this with your pencil, just kind of lightly. Definitely don't do it dark, because when we start doing systems of these, we're going to have to erase parts of them. But for right now, we're done. Now all that's left to do is double check with a point. So I'm going to pick a point that's well within this shaded region and see if it makes this inequality balance. So I don't have any super convenient points to work with. Maybe pick something on the x-axis so that you get at least one 0 in there. So 0, -5. Let's plug that in. So -5 is less than 1/5 of 0 minus 4. -5 is less than, this term cancels, -4. Is that true? Would you rather have $4 of debt or $5 of debt? This is true, so that's our double check. And all it really tells us is that we shaded the correct side. We're not entirely sure about this line. That's why we just got to be really careful when we're graphing it, not to make mistakes there. All right, let's try it again. So I ignore that symbol for a second. It's still in mx plus b form, so I can plot using the y-intercept and the slope. The y-intercept is 3. The slope, when we have just a negative in front, that means the slope is -1, which means go down 1, right 1. Down 1, right 1, down 1, right 1, all the way across the graph. Or reverse it, up 1, left 1, until we go off the graph that side. Now it is a less than or equal to, because it has that or equal to, we want to include this line as part of our solutions. So I'll connect that up with a solid line. And now because it's a less than, we're going to shade below this line. So we're going to shade this region here. All right, and good enough. All right, now we've got one with just an x. So this kind of looks like the equation for a vertical line. So I can temporarily treat this just like the equation x equals -1 and put the points in for that line. Remember, hoi vux, x equals equations, create vertical lines. We'll put in a vertical line at -1. But now one of our steps gets harder because this line doesn't have an above or below, it just has a left or a right. So if it's a less than or a less than or equal to, shade left. It's kind of like the way that these are pointing. If it's a greater than or equal to, you're going to shade right. The rules for solid versus dotted line are the same. This is just a greater than, so dotted line here. It's a greater than. You can only use this if the variable is on the left, by the way, so make sure if the variable is on the right to switch it around. We're going to shade to the right, so we're going to shade over here. All right. Now we've got an inequality that looks kind of like standard form. We don't have a slope and a y-intercept to use right now, so we need to manipulate this inequality until it's in a quote-unquote mx plus b form. And that inequality in the middle could flip direction. The rules for that are the same. So here, I'm going to subtract x from both sides. I get 2y is greater than or equal to negative x minus 4. I divide both sides by 2. I'll divide each term by 2. Do a little rearrangement here. I get y is greater than or equal to negative 1/2 x minus 2. And now I've got a slope and a y-intercept to use. Notice if that had been a negative 2, I would have had to have flipped my inequality. But it wasn't, it was a positive 2. All right, point at our y-intercept, attach the slope. Make sure you go in both directions. We're going to pick a solid line because we do want to include the line itself in our solutions. And we're going to shade above. All right, we didn't do a double check on that last one, so let's do a double check on this one. I'm going to pick a point, maybe something on the x-axis like 0, 2. Plug it in. Is 2 greater than or equal to negative 1/2 times 0 minus 2? Is 2 greater than or equal to negative 2? Checks out. This one, it's useful to double check these ones too because they're a little bit unusual. Let's just check with like, this point right here. 3, 0, is 3 greater than or equal, or is 3 greater than negative 1? Yeah, that one checks out too. Okay, on to our next topic, which is piecewise functions. Here we have a piecewise function. It's a line that stops at some x value, and then another line that picks up at that x value. And one line ends with a closed dot, which means include that point. The other line begins with an open dot, which means don't include this line here. So if I wanted to know which line I was on at exactly negative 1, I'd be on this first line because it's the one with the closed dot. Okay, so what we want to do is treat these lines as if they went across the entire graph and write their equation. So I'm going to act like this does just keep going all the way across. And I can see that the equation for this line would be y equals, the slope is a 1, so I'll just say x plus 2. We have a y-intercept of 2. Let's maybe use a slope triangle to get the slope on this one. I'm going down 1 for every 2 I go over, so that gives me a slope of negative 1/2. The y-intercept, I think we can pretty confidently say it's negative 1/2, because if the slope is negative 1/2 and we count 1 unit over from right here, we'd just go down a half a unit. So it's got to be negative 1/2. So the b value here is also negative 1/2, making this line where should I write it? Up here, y equals negative 1/2 x minus 1/2. All right, and now we're going to use function notation. So function notation, you write f parentheses x close parentheses. We say this as f of x, and this just takes the place of y on the other side of our equal sign. Now we're going to use a curly bracket, and it's got to be big enough to at least fit 2 lines of math in, because we have 2 pieces to this piecewise. Next, we're going to copy in just the right-hand side of these equations. So the x plus 2 and the negative 1/2 x minus 1/2. All right, and then we're going to put a comma after both of these and use an inequality to express what values these equations are valid for. So this first piece goes up right up until the x value is equal to negative 1. So it's valid for x is less than or equal to negative 1. I did the or equal to because it's got the closed dot. this line takes over at -1, so its value for all x values greater than -1. Put a box around this whole thing because that's our piecewise function. So let's just label a few things here. F of x replaces y. This is just the right side of equations. And this is where the lines exist. But we only care about the x values for where they exist. We don't really care that this line stops when y is equal to +1, just that x is equal to -1 when it stops. All right, let's just keep practicing this. Here we've got another piecewise for you to pause the video and copy down. Next to each of these lines, I'm going to imagine that they both cross the y-axis so I can get a y-intercept. This is just the line y equals x. And this here, it's got a slope of +1/3 and a y-intercept of -1⁻⁻. If I count over from maybe this point backwards, with a slope of -1/3 going that way, hit it. -1⁻⁻, so y equals 1/3 x minus, I'll say 4/3, so I'm not dealing with mixed numbers. All right, we're going to write f of x, curly bracket with room for two pieces. And when we write the right-hand sides, you want to do the pieces left to right. So I'm going to do the 1/3 x minus 4/3 first, because that's the first piece, if we're traveling left to right, that we would be traveling along, and then we would jump to this piece here, which is just an x. Once I drop that y, this first piece is valid for all x values less than 1, and then the second piece takes over when x is greater than or equal to 1. Notice where the closed dot is. And that's it. You don't close those curly brackets, they just stay open. All right, another one. This looks like the line y equals -x. If I continue it going, it looks like it would cross the y-axis at a -2. This line here is y equals 1/3 x, slope of 1/3, and it's crossing, again we have to use got to count by thirds, so 2 1/3, but 2 is 6/3, so 7/3. Now we're going to write out the function, so it's f of x, curly bracket, just the right-hand side's going left to right, so -x minus 2, 1/3 x plus 7/3, comma, comma. This first line is valid right up until x is greater than -1, so it's for x less than or equal to -1, and then when x is greater than -1, the second line takes over. Box that whole thing. All right, now we're going to graph it. So first thing we want to do is we want to pay attention to this number at the very end. I call this our transition value. Did I make it look like I'm not? Do it like this, arrows. So I call that value the transition value. Transition value. So what we're going to do is we're going to do a vertical dotted line at each transition value. Okay. These lines are not part of the actual graph. They just help guide us. So a dotted line is never part of a graph. It's always just sort of a guide, even like when we were doing those linear inequalities. It was just a boundary that we're not included. So this is going to help show us where we switch over from one line to the other. And I say this cuts the graph into two strips. You've got strip 1 over here, this more narrow one, and strip 2 over here. All right. And so we want to graph the lines you're going to graph it across the graph, but then only keep the part that's in the strip that it's valid for. So I don't want to say this. You want to graph top to bottom in terms of the equation. So this one first, then this one, and then if there's more, we would just keep going down. So top to bottom, left to right. One line per strip of graph paper. Okay, so this first one, remember we cut the y off, we're going to add that back in. So this is the equation y equals x plus 2. So that's got a y-intercept of 2 and a slope of 1. I can start it going this way, but we're not going to keep this part of the line. Let's reverse that, go down 1, left 1, all the way back until we're into strip 1. And then we're only going to keep this part here, right up to the boundary value. And then right at the boundary value, we have to check. So should we include this point based off of that inequality right there? Well, that doesn't have the or equal to, so this is the one that is left open. And then where this line runs into our dotted line, it's going to get the closed dot. So there is piece number 1. That is the line y equals x plus 2, but it's only valid up until x exceeds -4. And now this is the line y equals 6. That's a horizontal line that crosses at 6. And we already decided that it gets the closed dot because it has the or equal to. And there's our graph. All right, let's try a little bit more complicated one. So first, look at the transition values. We're transitioning at -4 and 1. Let's add in those vertical dotted lines at -4 and 1. All right, and now left to right, top to bottom, or top to bottom, left to right. So let's take this first one out. That is just the line y equals -x minus 4. So that's a y-intercept of -4. A slope of -1 would take us this direction, but I just want to back it up until it's into strip number 1, and then only keep this section here. This has the or equal to, so let's put a bold dot at the end of that piece and then erase that over there. Now on to strip 2 and equation 2. We'll do this in a different color. This is the line y equals the absolute value of x plus 1. This is a v-shaped graph that's been moved. Let's even write this. That moves us left 1. So v-shaped graph that's been moved left 1. And I'll switch back to red. There's a vertex right there. But I'm going to stop it when it hits the boundaries. Connect these up. And then check to see, and it's going to be open dots on both sides. So I like to do this. I make a big dot and then make it clear that it's open in the middle. Okay. Now on to the third strip, so third equation. We'll break that one up out down here. This is the y equals the absolute value of x. So v-shaped, but hasn't been transformed at all. So we're just going to keep, we don't even see the vertex. We're just going to keep the part that takes up here and keeps going this direction with a slope of 1. And it gets to start with a closed dot because it has the or equal to. There's our 3 pieces. So we're just graphing 3 equations on one piece of graph paper, but only keeping a small part of each. All right, I'll embed a few more questions here. That's the end of this lecture video. Try a few more and have a good rest of your day.